So here's the relativistic slide rule. It's a Euclidean geometry. So how do we go from that to hyperbolic geometry? What happened? Well, Einstein was just using Euclidean geometry. Euclidean geometry when he came up with special relativity. So he would have done something like that. And I won't go into the details. You can just study that. It's all pretty self-explanatory. You can just plug the numbers in. The transformations, Lorentz came up with the same transformations to explain the Michelson-Morley. So his was just length contraction, which is just gamma is just 1 over length contraction. So Einstein was more thinking about a light clock moving to the right, and if the speed of light is constant, then it's going to have a longer path, and because it's got a longer path, it's going to tick more slowly, because according to the frame that's not moving, the moving clock will run slow. Okay, and that's undistorted, so you can just measure those lengths and you'll find out what they are. But Minkowski was Einstein's teacher, maths teacher, and he was a mathematician, so he went, well, we should join L and T together into one space-time. And so he said, you should have like a light clock. And what he meant was you should have hyperbolic geometry. So the circle gets replaced with hyperbolic geometry. And then everything's distorted from then on. So that's what the relativistic slide rule would look like in the distorted Minkowski space. I'm not sure what you'd call that, some sort of pseudo Riemann manifold or something, I don't know. But anyway, you can't come up with that unless you have the relativistic slide rule, which is that. That's the only way to figure it out. So anyway, you got your light cone, and in the distorted version you'd have velocity increasing like this, which means that let's go back to 0.6, which means that there's gamma there, so it's like the bottom of the light clock and the top of the light clock is like they've separated to a distance of 1.25 units. So the speed of light doesn't change, so it just takes longer to get to the top of the clock, basically. And of course, at the speed of light, gamma is going to go all the way up, and this is gamma, the top of the clock, just heading up, and of course you're never going to get to the top of the clock at the speed of light, so time will stop. Okay, whereas in the rest frame, in your own rest frame, the top of the clock is just 1 unit away. Alright. So that's, I could have just graph everything like that, and then I can just take the derivative For example, at a velocity of 0.6, you can just read off all the values. But the question is, how do you come up with this without the relativistic slide rule, without Euclidean geometry? So the way I see it is that general relativity is like a topology. It's like an emergent topology, but underlying it is still is special relativity still, which so that you get curvature. Eventually, you get this curvature, but space-time is actually straight. That's space-time there. Just gets shorter, and that causes curvature. And yeah, so I mean, it correctly calculates the mass of the W boson, not to mention all of the other outstanding problems in physics, which I've been into in other videos.